So you already saw some of this today and we talked about it in class, but I kind of felt it was important to just kind of do an entire video based off of what we talked about today in class, which is going to essentially be electron configurations and electron spin. So in electron spin, what happened is somewhere around the 20s when we discovered the electron, once we figured out what the electron was, we were able to then go ahead and decide and figure out a little bit more about how the electron actually operated. So what we did is we took a hydrogen generator and made some hydrogen atoms, and we took those hydrogen atoms and we shot them at a plate that had a small slit in it, and the small slit in it had concentrated a beam of electrons and hydrogen atoms with the one electron in them, and it passed through this plate, and then it passed in between the beam itself, in between two magnets. One was a negatively charged magnet and one was a positively charged magnet. The electrons that bent, or the hydrogen atoms with the electron that bent toward the positive magnet, we labeled as negative electrons, and the ones that bent toward the negative magnet we labeled as positive electrons. And I know you're thinking, well, wait a minute, aren't all electrons negative? And the answer to that question is yes, all electrons are negative. However, when we put them into their orbitals, which is where they exist around the nucleus of the atom, one of the things that we thought about was that if we had an electron that was arrow up, two electrons, ideally, because they're both negative, they would repulse each other and not want to be anywhere near each other. So if they were negative, positive, they were up, or down, they would still repulse each other and not want to be anywhere near each other. Well, what we found out though is that because we have the orbitals like the s orbital, which is spherical, the p orbital, which is dumbbell shaped, right? Those all hold two electrons, and the only way for those electrons to exist in that space at the same time is if they were opposite spin. So when we say opposite spin, what I'm getting at is that they're still negative, but they are sort of orientating or rotating slightly opposite so they can stand to be next to each other. So we've now decided or learned that we call this the quantum number. The spin quantum number, and basically that tells us that if we take two electrons and we put them in the same orbital, they have to be spinning in the opposite directions. We don't need to concern ourselves too much with the quantum spin number, in large part because the College Board has taken out the ability to identify an electron down to its half plus or half minus value, but I still think it's important that you're aware of it, because what ends up happening is when we talk about the orbital diagrams, like we will in a second, what we'll have electrons that want to pair up, and they pair up sort of like this. They cannot pair up like this, because if they do, they will repel and not stay together, and then the orbitals won't work. So the electron configuration are a couple of things that we talked about last year in Honors Chem. So just to kind of talk about it a little bit, if I talk about something like magnesium, for example, magnesium has 12 electrons. And the rules that we have to follow are really specific about what the electrons are allowed to do. So the first rule is the off-ball principle. The off-ball principle basically says that electrons have to follow a prescribed pattern when we are tracing them around the nucleus of an electron. So the off-ball principle basically says they're going to go, and the electrons are going to be put, like, for example, in the 1s, and then maybe the 2s, and then it jumps into the 2p, and then it goes from the 2p to the 3s, and there's a very specific pattern that they have to follow. Hund's rule talks about the fact that all electrons, when they enter into an orbital, they go in opposite. They all go in one spin direction, and then they come back and they re-go in a different spin direction. So what that really talks about, or what that really means, is that in Hund's rule, we're basically saying that in the 2p orbital, if I'm going to try to fill that up, and remember that those can hold a total of 6, but each orbital can hold 2, I'm going to go half, half, half full, and then come back and do half, half, half full. So that's the Hund's rule. And then the Pauli exclusion principle says that no two electrons can have the same set of quantum numbers, and one orbital can hold at most two quantum numbers. So if I'm talking about the S, arrow up, arrow down, one of them is going to be a plus 1/2, and the other one is going to be a minus 1/2. Even though the rest of their electron configuration might look identical, that's what distinguishes one electron from another. So your job in all of this is to be able to look at the Aufbau principle, make sure that the electrons are being placed in the appropriate order, make sure that we are half filling orbitals before we completely fill orbitals, and then make sure that there are arrow up and arrow down so that they're in opposite directions. So the couple of different ways that we write the electron configurations would be, and I'll talk about magnesium again, which was 12 electrons. In orbital notation, what we do is we say every electron is going to fill a 1s, and it's going to go arrow up, arrow down. And then from the 1s, we would go to the 2s, which is arrow up, arrow down. And then from the 2s, we go to the 2p. And that's arrow up, arrow up, arrow up, and then arrow down, arrow down, arrow down. And then lastly, we would go to like 3s, which is arrow up, arrow down. And then that's magnesium. And each arrow represents one electron. So if I were to, so that's our orbital notation. Our electron configuration for this particular atom would be 1s2, 2s2, 2p6, 3s2. So that would be our electron configuration. Now, the noble gas is the condensed notation by which we go ahead and we look at the periodic table and we take a look and see where the electrons are located, or not the electrons, the noble gases are located in front of the one that we're trying to deal with. So here's an example for you. I have barium, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. If I look at the periodic table and I find barium, and then I go ahead and I go back numerically speaking until I find the noble gas, so I'm basically subtracting electrons one at a time, the electron configuration that this best exemplifies is xenon. So xenon is the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. And then we write xenon, we put it in brackets, and then we put 6s2 after it because that's the rest of it. And then that covers all of the things that we need to be concerned about when we talk about the idea of the noble gas shortcut. So as an example, we might talk about phosphorus. Phosphorus has 15 electrons. So if I were to draw the orbital diagram, I would go 1s, arrow up, arrow down, 2s, arrow up, arrow down, 2p, 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 arrow up, arrow up, arrow up, arrow down, arrow down, arrow down, 3s, arrow up, arrow down, 3p, 3p, 3p. So at this point, I've placed 2, 4, 10, 11, 12, and I've still got 3 more to go. So I'm going to go arrow up, arrow up, arrow up. I'm going to spread them out. So when I write the electron configuration, my electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. So that's the electron configuration and orbital diagram for the element of phosphorus. There are a couple of exceptions. For example, copper, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. However, a more stable arrangement for copper is to simply take one of these electrons and place it here. So it would look like this, 4s1, 3d10. Now, I'm going to skip ahead for a second just so that we can take a look at the stable. So what ends up happening, like I said, is one of these electrons from the 4s is passed down to the 3d, and when that happens, we now have a more stable arrangement of electrons. And another one that this happens for would be cobalt, or chromium rather. And again, we have the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So what's going to happen is one of the electrons from the 4s2 is going to go down to the 3d level, so it'll be 4s1, 3d5. This creates a more stable arrangement because what ends up happening is that in this case, 3d, 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 each of the orbitals of the 3d sublevel have one electron. That's more stable than having the 5 3d orbitals and having one of them open. So this becomes a more stable arrangement of electrons as well. So like I said, it's kind of trying to obey Hund's rule, sort of, but table. At the periodic table, here's copper. Copper almost completes the D sublevel, and by almost completing the D sublevel, if it did complete the D sublevel, it would be a little bit more. It has to do with the fact that where these guys are on the periodic table. So chromium, well, it doesn't have. That's not the fact, but the fact of the matter is that by moving an electron from the 4s2 to here, chromium becomes arrow up, arrow up, arrow up, arrow up, arrow up, and that's more stable than having that one 3D open. So hopefully that makes sense. Now, when we write electron configurations for ions, what we have to keep track of, or what we have to think about is that one thing that we have to remember is that when electrons, oh boy, that doesn't even make sense, CTRONs, are lost, the ion becomes positive. So it's a cation. And when electrons are gained, the ion is negative, we call that an anion. So when that happens, though, the atom itself gains an electron or loses an electron, and then its electron configuration appears to take the shape or the form of another atom on the periodic table. So here's some ones down here that I want to talk about. And I have neon. So neon has 10 electrons. So its electron configuration would be 1s2, 2s2, 2p6. Okay. Aluminum has 13 electrons. So aluminum's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p1. So if this electron and these two electrons are transferred away, we now have neon's electron configuration. Another example would be nitrogen. Nitrogen's electron configuration would be, because it has 7 electrons, 1s2, 2s2, 2p, let's see, 3. That sound about right? 1s2, yep, that's 3. Okay, so what ends up happening is that this guy, nitrogen, will gain 3 electrons to become 2p6, which again is the same electron configuration as neon. So all of the ones that are listed here have the same electron configurations as neon, and that's a special term that we have that we call isoelectric. So an isoelectric element is something that has the exact same electron configuration as another element based on the gaining and losing of electrons. Which brings me up to the idea of something that we call diamagnetism and paramagnetism. So with diamagnetism, we have a sample of an element, and that sample of an element or a compound is put into a magnetic field, and it doesn't do anything. It doesn't get pulled one side or the other. Okay, and it has to do with the fact that it has all of its electrons are already paired up. So, for example, zinc. Zinc's electron configuration. So zinc's number of electrons is 30. So the noble gas, because I'm going to try to make this a little bit easier on myself, that directly becomes in front of zinc is argon. So argon, and then zinc after argon would become 4s2, and then it would be 3d, arrow up, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down, arrow down, 3d10. So zinc won't react or deal with the magnets in any way, shape, or form because all of the electrons in its electron configuration are paired up. Iron, on the other hand, also has a noble gas shortcut of argon, and in this case iron is a +3 ion. Well, that'll be important in a second. So when I go to write its electron configuration, it's 4s2, arrow up, arrow down, and then it has 1, 2, 3, 4, 5, 6 electrons in its d orbital. So 3d, 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 1, 2, 3, 4, 5. So I'm now going to go ahead and add the electrons. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So now what I'm going to do is I'm going to say that it lost 3 electrons in that d sublevel. And by doing that, what ends up happening is that now not all of the electrons in this particular element are paired up. And because they're not paired up, we would call this paramagnetism. So diamagnetism occurs when an element has all of its electrons that are paired up and it doesn't react to a magnet. And paramagnetism occurs when an element does not have all of its electrons paired up and it does react with a magnet. So taking a look at some examples here. Vanadium. So I'm going to start here. So vanadium +3. Vanadium by itself has 23 electrons. So if I were to write its electron configuration, starting with a noble gas shortcut, which would be argon, and then it'd be 4s2, arrow up, arrow down, and then 3d, 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 okay, and then so that's 4s2, and then arrow up, arrow up, arrow up. And then what's going to end up happening is that because it's a +3, it's going to lose 3 electrons. So in this case, this particular element, or ion rather, would be diamagnetic. Because all the electrons remaining are paired up. Cobalt by itself has a total of 27 electrons. So because it happens to be in the same block and row as vanadium, argon, and then 4s, arrow up, arrow down, and then the 3d, 1, 2, 3, 4, 5, and since it's element number 27, it would be 1, arrow up, arrow up, arrow up, arrow up, arrow up, that's 5, arrow down, that's 7, so now we have 27. And then because it's in ion, it's positive ion, it's going to lose 1, 2, 3 electrons, and when it loses 3 electrons, not all of the electrons are paired up this time, so that makes it paramagnetic. And then another example would be silver. Silver has 47 electrons when it's neutral. I'm going to use the noble gas shortcut for silver, which would be krypton in this case. So then I would have 5s, arrow up, arrow down, and then it'd be 4d, And then because of where silver's at, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 electrons. So arrow up, arrow up, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down, arrow down, arrow down. So that's the electron configuration for silver, and it's going to lose 1 electron. Oops, I got carried away. I put too many on there. So now it's going to lose 1 of its electrons. So now I have a situation where not all the electrons are paired up again, so it's also paramagnetic. And the College Board has a tendency to put at least one question on the exam, either in the multiple choice, usually in the multiple choice, about diamagnetic versus paramagnetic. So just something to keep in mind. Okay, then we also have these last couple of examples in terms of trying to evaluate whether or not these electron configurations are in the ground state, or if they're in the excited state, or if they're not allowed. Well, let's talk about the ground state and excited state and all that stuff first. So ground state means that all of the electrons are in their most stable arrangement. Okay, and then excited state one of the electrons is moved to a higher energy level. And then not allowed would simply mean that the electrons don't follow the Aufbau principle. So if we take a look at these examples, in the case of the first one, I see that it's 1s2, 2s2, 2p6, 3s1, 5p1. Now, one might argue that this is not allowed because it doesn't follow the normal pattern, but I would argue that it is an excited state because one of the 3s electrons jumped up to the 5p energy level. Okay. In the case of the next one, I see 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Now I'm going to say that this is in its ground state. I can see how somebody might argue that it's in its excited state, but I'm going to say it's in its ground state because even though it doesn't quite follow the pattern, we can make the assumption that one of the electrons from 4s came over here and dropped down to the 3d sublevel, and because it dropped down to the 3d sublevel, it became a much more stable arrangement. The next one is 1s2, 1p2, 2s2, da 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 da. This 1p2 is actually impossible. We cannot have a p sublevel in the 1s in the first energy level, so this makes it not allowed. And then the last one is pretty boring. It's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. Nothing seems out of the ordinary there, so that makes this ground state as well. So, after you've watched this video, you should be able to definitely complete questions 6.68, 69, 70, 71. You'll have a little bit of time in class to work on that tomorrow. So take a look at it tonight and then maybe see if you have any questions, and then we'll start probably talking about that in class tomorrow. Have a good night.